The next section talks about stretches of functions. So a stretch, and the opposite is a compression, are transformations that cause functions to change shape. Up till now we've just been moving them. We've moved them up and down and side to side. Those are translations. And we have mirrored them, flipped them from one side to another, either in the y-axis, in the x-axis, or sometimes in both, which kind of look like a rotation. Stretches and compressions are transformations that actually change the shape, the spacing between the points. A stretch is a transformation that, this goes on, this elongates. So if you imagine we had a little square happy face, if we stretched it vertically, it would look like this. If we stretched it horizontally, it would look like this. So this is a vertical stretch, and this is a horizontal stretch. Formally, a stretch is a transformation that results in the distance from the x-axis growing by a scale factor greater than 1. We call that a vertical stretch. Or the distance from the y-axis of every point growing by a scale factor greater than 1, which is a horizontal stretch. A compression is a transformation that results in a squish, if you will. This is a squish. So if you're going to squish something vertically, if it was a perfectly square little thing and you squished it vertically, imagine sitting on it, it kind of pancakes. That's a vertical squish. A vertical compression or horizontal compression would look like this. So really it's just getting closer together, either closer to the x-axis or closer to the y-axis. So here's where we get a little bit lost in the math babble. The graph of g of x equals a f of x, so that means our new graph is the same as our old graph times some sort of number, as long as this number is greater than 0. So it's got to be a positive a. Positive. This is a vertical stretch or compression of the graph f of x by a factor of a. So let's think about this. Why does it have to be positive? Well, last lesson we learned that if the number out here is negative, it's not a stretch. We called that a reflection. That was when it was mirrored, either in the x-axis or the y-axis or whatever. It's got to be a positive number. If it's a negative and it's a number, well then it's a stretch and a reflection. If a is greater than 1, then the graph is vertically stretched by a factor of a. If a is between 0 and 1, the graph is vertically compressed by a factor of a. Similarly for the horizontal, instead of having an a in front of the function, we're going to call it a k, and it's not in front of the whole function, it's just in front of the independent variable. The graph of g of x, our new graph, is the same as our old graph as long as k is greater than 0. Again, for the same idea, if k is negative, then it's a reflection. This is a horizontal stretch or compression of the graph f of x by a factor of k. If k is greater than 0, it's a horizontal stretch by a factor of k. If k is between 0 and 1, then the graph is horizontally compressed by a factor of k. Our first example, given the function f of x equals square root x, this is one of our favorite base functions. The square root function has points 0, 0. So let's do these ones in black. We've got 0, 0. We've got 1, 1. Let's add a few more. 4, 2. 9, 3. And we've even got, we can go all the way up to 16, 4. Given the function f of x equals square root x, so here's our f of x, write an equation that represents g of x and 8 of x and describe the transformations. Then transform the graph of f of x to stretch the graphs of g of x and h of x and state the domain and range. And we've got 1, 2, 3, 4 different ones we're going to do. So we'll do each one in a different color. So this is how I'm going to recommend to do this. Let us do this first g of x. So we're going to have our x values. So what x values do we usually use for square root functions? Well, the ones that are picked on this graph anyway are x equals 0, x equals 1, x equals 4, x equals 9, and x equals 16. What were our values for f of x from our original function? What are the other coordinates? 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. So x and y, I've just really written out the coordinates. What is our new function? Our new function is every y coordinate, and we're going to multiply it by 2. So it's going to be f of x, and we're going to multiply by 2. So we take our f of x, 0, 0 times 2, still 0. 1 times 2, 2. 2 times 2, 4. 3 times 2, 6. 4 doubled is 8. So now these are our coordinates, 0, 0, 1, 2, 4, 4, 9, 6, and 16, 8. Let's go for it. 0, 0, still there. 1 is now 2. 4, 4. 9, 6. And 16, 8. 16, 4, 5, 6, sorry. 4. 6, 7, that's not even on the graph. Oh well. So this is our g of x. And it would continue past there. I'm too lazy to draw it. Transform the graph and describe the transformation. So this is definitely a vertical. It's definitely up and down, not side to side. We've changed the y coordinates, so it's a vertical change. It's a vertical, is it a stretch or a compression? Well, 2 is bigger than 1, so it's a vertical stretch by factor of 2. Let's try our next one. H of x. So we're going to set up the same sort of table. We're going to do the first one with our base function. So these are our base function. We had 0, 1, 4, 9, and 16. 0, 1, 2, 3, and 4. Oops. Sorry about that. They don't quite line up. There we go. Our new function is now h of x, which is 1/2 of f of x. So that means any y coordinate, we're going to divide by 2, or multiply by 0.5. Either way you want to think about it. So we're going to do 1 over 2 multiplied by 0, oh, still 0. 1 over 2 multiplied by, oops, 1, 1/2. I'm going to put it as a decimal, usually easier to graph. 2 times 1 over 2. Should know this. Only 1. And this one's going to be 3 times 1 over 2. 1.5. And this one's going to be a 2. So these are the points I'm now going to graph. So the points I'm going to graph are, let's do it like this. Our 0, 0 is still 0, 0. That's going to get a crowded point. 1 and 1.5. 1 and 0.5. 4 and 1. 4 and now 1. 9 and 1.5. 9 and 1.5, and 16 and 2. 16 and 2. So our new graph looks something like that. This is our h of x. So what kind of move is this? This is definitely still vertical change. We've kind of squished this one down, so it's a vertical compression. It's compressed by a factor of a, So if a is between 0 and 1, as it is when we have a 0.5, the graph is vertically compressed by a factor of 1/2. So I'd like to look at an example of horizontal stretches, or horizontal compressions. Given the function f of x equals square root x, write the equation to represent g of x and h of x described over here, and describe the transformations. Then transform the graph of f of x to sketch the graphs of g and h, and state the domain and range of the functions. So here we have our basic unmodified square root function, points of 0, 0, 1, 1, 4, 2, and 9, 3, and this one seems to go all the way out to 16, 4, and beyond. So this is my f of x function, my basic parent function. I want to take my basic parent function, our f of x, and change it into g of x, which is f2x. So this f can be replaced by square root. So this means g of x, I'll do them in pink, g of x is going to equal, instead of f, I'm going to do square root 2x. This is my new function. What kind of transformation do I see here? I see a vertical, it's inside, this is the k position, I see a horizontal compression. Horizontal stretch. It's bigger than 1 by 2. Alright, so my basic way of doing stretches is to use a table of values. So let's start with our base function, x and f of x. X is our 0, 0, next one is 1, 1, this is 4, 2, here we have 9, 3, and I've got 16, 4. Sorry about that. So I went along, here's the 16, 4 point, 9, 3, 4, 2, 1, 1, 0, 0. Alright, so if I take a look at g of x, I know that I want to make a horizontal change. X is our horizontal, f of x is what goes on the y-axis, it's vertical. Since I want to change horizontal, I'm going to work with the x's. So my new table of values is going to have a different x, but since there is no vertical change going on here, there is no a term here, doesn't say 2, doesn't say -1, doesn't say a half in front of the f. This means that all of my f of x terms are going to stay the same. All of my y coordinates, if you will, are going to stay the same. What's going to happen to my x? Well, my x's has to change by a factor of 2. Just to be difficult to make this process work, we have to multiply each of our x's, not by 2, as one would assume, it's by a half. Think of it. 2 is the same as 2 over 1. If it was a fraction, it would be 2 over 1. When we multiply anything on the x, the independent variable, we have to multiply by the reciprocal. The reciprocal, flip the fraction, 1 over 2. So that means 0 stays 0, 1 becomes 0.5, 4 becomes 2, 9 becomes 4.5, 16 becomes 8. So that means my new stretch, my new g of x, the points are 0, 0, a half, and 1, 2, 2, 4.5, and 3, and 8, 4. 8, 4. So here is my g of x. Let's try h of x. My h of x, well, again, this f is the same as square root, so this is going to be the same as the square root of 1/2 times x. This is going to be a horizontal compression by 1/2. So to do this, we're going to take our same base function, we take our same original function, our x versus f of x, 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. And we're going to change it. In this case again, we've got a k term. This k term is telling us that our x is going to become, so we were going to be 1/2, k equals 1/2, that way so we multiply by 2 over 1. We multiply by the reciprocal of the fraction. Our f of x is going to stay the same. So we're going to copy these numbers right here, 0, 1, 2, 3, 4. Here we're going to take each of the x's and multiply by 2 over 1, just multiply by 2. 0 times 2 is 0, 1 times 2, 2, 4 times 2 is 8, 19 times 2, 9 times 2 is 18, 16 times 2 is 32. So we're not going to have the space to graph all these. Let's do it. This time we'll graph in purple. Alright, so if our h of x is going to be these points, let's give it a try. 0, 0 is still 0, 0. We're going to go to 2, 1, 8, 2, and 18, 3. So this is what we call a horizontal compression.